Hello again, and I'm going to talk today about correlation and linear regression, which in your textbook is actually, there's an error on the publisher's end where in the table of contents, this chapter is listed as chapter 12, but the actual chapter in the body of the book is chapter 13. But either way, the thing to remember is that you're going to look for the correlation and linear regression chapter. And just so we're on the same page, let me tell you the page number that we begin this from. So this would begin on, this is page number right here, on page 390. So page 390 is the beginning of the chapter on correlation and linear regression. And in this chapter, we'll review everything apart from the very last two parts to the chapter, which look at calculating and interpreting confidence and prediction intervals and log functions for transformations. But I'm going to focus in this video on explaining what a correlation is and why do we go into correlation analysis. And then we'll do some actual, an example of a correlation analysis, and then look at what's the correlation coefficient and how do we interpret that. And then after that, we'll go into a discussion of linear regression and how does that differ from a correlation analysis. Okay, so let's get started with the correlation analysis. So correlation is basically that experimental process of trying to determine whether there's some relationship between any two variables of interest. Okay, I might be interested in determining if, for example, the amount of rain within a given season has a relationship to the crop output that farmers within a given region would be expected to have. Or as examples on the PowerPoint show, a company might be interested in determining whether the amount that a company spends on training actually has a relationship to the company's monthly sales. Okay, so correlation analysis is just basically that. We're trying to find out whether there's a correlation or whether correlation exists between any two variables of interest. Okay, and once we determine that an relationship exists, I'll be interested in determining is what's this direction of that relationship. Is it a positive relationship where if one variable increases, the other one increases? Or is it a negative or an inverse relationship where if one variable increases, the other one decreases? Or is there no relationship at all? Okay, I'll also be interested in determining what's the strength of that relationship. And the reason for that is, yes, we could have a positive relationship, for example, but that relationship might be weak to an extent where it doesn't really, it's not significant. Okay, so I'm interested in the direction of the relationship and whether or not that relationship is strong, moderate, or weak. Okay, so let's go into the process that we would have to take to be able to do a correlation analysis. And one of the very first steps is to visualize your variables. Okay, so let's look at this example here where we have companies, sales representatives, and the company wants to know if there's a relationship between the number of sales calls that the representatives make and the total number of copiers that those same representatives sell. Okay, so the first step for you when you run your correlation would be, given that you're business students, I'm hoping that you're comfortable enough with Excel to go into Excel. I've uploaded that information from your PowerPoint slides to Excel. And I'm going to throw in a scatter diagram by highlighting my data and going to insert. And then I can either do a recommended chart and look for the scatter diagram, which is the first one given there. Or alternatively, I could look for the scatter diagram, which is right over here within the charts. So let's click on our scatter diagram. And this gives us a visualization of what the relationship is between the number of sales calls and the number of copiers sold. Okay. Now, if I try and visualize this, what I see here and what hopefully you all see here is that there seems to be some type of a relationship. And one way of doing that is I could try and throw in a trend line and try and see how that trend line would look. Let's just throw in a trend line real quick. And that right there tells me that, yes, it seems to be a relationship where the more the number of sales calls, which is what our x-axis here is, the greater the number of copiers sold. Okay, and that's what's to be expected. If I'm in sales and marketing, if we make more calls, reach more customers, we should expect to sell more copiers. Okay, but just by visualizing this, I cannot tell the strength of the relationship. I see there's a positive relationship, but I cannot just automatically say yes, it's a strong relationship. I need to dig into this further and try and figure out, okay, what's the extent of this relationship between these two? Okay, so let's dig deeper into our data and try and come up with additional information. Okay, so in correlation analysis, one thing that we usually look at is how many data points are above or below a mean value. Okay, so to explain that, let me quickly throw in the averages for this number of sales calls equals average, and I'll highlight all these. And I'll do the same for the number of copiers sold, the average number of. So I get these two numbers here. I get a 96 for average number of sales calls and a 45 for the average number of copiers. Now, I'm just going to insert a line here just for visual reference. Insert shapes, insert a line. All right, so the first line that I'm going to insert is the average number of sales calls, which would be somewhere right about here. Says you have an average of 96 calls. I'm going to change that color so it's different. And the second line that I'm going to put in here is the average number of copies sold, which is giving us 45. So I'm going to put my second average value here, 45, somewhere about there. Okay. And now, for the purpose of correlation, I'm interested in seeing if it's a positive relationship. I expect to see most of the values being in this lower quadrant at the bottom right here and the upper quadrant right here. If, on the other hand, we have a negative relationship where as one variable goes up, the other variable goes down, I'd expect to see a whole bunch of data values in the upper left-hand quadrant and in the lower right-hand quadrant that we have here. Okay, but in this case here, I see that our data points fall mostly into the lower left-hand and the upper right-hand quadrant, and that tells me that we have a positive relationship. Okay, so now we want to go ahead and try and determine what's the nature of that relationship in terms of how strong is that relationship. Okay, so when to do that, we need to calculate what's called the correlation coefficient. Okay, and the correlation coefficient is a number that ranges from a -1 for a very strong negative relationship to a 1, which is a very strong positive relationship. Okay, if we have a 0, it just basically tells us that there's no relationship between the two. And one way to visualize a 0 would be, let me go back into my spreadsheet. A 0 would be if I had data points along, for example, this mean value of 45 here. So if I had, let me throw in some data points here. So if I had one point there, let's change the color to make it stand out. So assume I had data points all over the place, but with no trend, no specific pattern to it, then we'd say that the number of sales calls doesn't really impact copiers sold. Okay. With the example that I'm putting up here, I see that I'm making more sales calls, but the number of copiers sold remains the same. Okay. So in that instance, it tells us that there's really no relationship between the number of sales calls and the number of copiers sold. Okay. So if I make 1,000 calls and I still get the same 45 number of copiers sold, as if I just made 2 calls and I still got 45 copiers sold, then that tells me that there's really no relationship between these 2 variables, and I might want to look elsewhere to try and figure out what is driving copier sales. Okay, so that's something that our correlation coefficient should enable us to do. Okay, so the correlation coefficient tells us the strength of that relationship and the direction of the relationship. The negative value means that we have a downward slope from your upper left-hand quadrant to your lower right-hand quadrant. A positive value tells us that we have an upward sloping curve from your lower left-hand to your upper right-hand quadrants. Okay, so now we want to go into how do we go about calculating that correlation coefficient that is listed as R. Okay, so we're interested in finding this value here that we call R. Okay, so question that becomes, how can we determine the strength of this relationship? So let's first of all do it the long way, and then I'll show you the shorter way of doing this. I believe it's important for us to be able to understand the logic that goes into what Excel is going to do for us on the back end. Okay, so for us to be able to determine how many what R is, I'm going to have additional columns here that will enable us to calculate that value. So the first column that I'm going to have added to this is column D, and in column D, I'm going to add the difference between our sales call value and our average that's given here. Okay, so I'm going to basically take this value of 96 minus the 96 that we have here for average value. Okay, now before I hit enter, I'm going to hit F4 to change this and to hold it constant so that I can drag that formula down. Okay, so that way if I'm dragging the formula, it's not taking me past where our averages are over here. Okay, and I'm going to do the exact same thing for the number of copiers sold. I'm going to take the value here, subtract the average from it, and that's going to give us a value that we call y minus y bar. Okay, so here we have for Brian, he sold 41 copiers. We subtract the average of 45 from that value. Again, I'm going to hold this constant by hitting F4 on your keyboard, and you have to see those dollar signs, and you know that it'll always reference this cell in yellow. Okay, so if you did this right, if I was to sum this up, it should sum up to 0. Okay, if you did the auto sum, you should have a sum of 0 at the bottom. Okay, and the reason why that is because we're basically assuming that that average line, there's going to be half the data points are going to be above the mean, half the data points are going to be below the mean. So when we sum it up, it should average to 0. It should sum up to 0. Okay, so now we don't need the zeros at the bottom here, that's just for illustration. But so now we have our x minus x bar and y minus y bar values. The next thing that I want to do is multiply these two. And remember, what we're trying to do is calculate our correlation coefficient, which is given by the formula that I have here on your top right-hand side. So I'm just basically trying to calculate our correlation coefficient, which is our measure of the strength and direction of the relationship. Okay, So the next thing that I want to do is multiply columns D, the values in column D, by the values in column Y. And let me just use a concatenate. Concatenate, that's just being lazy trying to type that information. So I'll use this to type those two. One moment. Equals concatenate X bar. You don't have to do this. I just didn't want to type in all that. So I just merged those two cells together and it gave me that heading. All right, so I want to multiply our value here by our value in column E. Okay, and then drag that formula all the way down. Okay, and the next thing that I'll do is sum this up. Column F, if we sum up column F, it gives us a value of 6672. Okay, now this value here is the same value that we have. This is what we have in the top, in the numerator of the correlation coefficient formula. Okay, so we've calculated the sum of x minus x bar multiplied by y minus y bar, and it gave us a figure of 6672. To that, I'm going to have to figure out what's the standard deviation for our x values multiplied by the standard deviation of a y value of our y value variable, and then multiply all that by a sample size minus 1. Okay, so let's start. How do we calculate the standard deviation of columns B and C? Well, we're in Excel, so I'd like you to be comfortable using the functions that you're going to have in Excel. So let's highlight these two columns here, and let's throw in, let's go into data analysis, and I'm going to go to descriptive statistics. Okay, and once I click on the descriptive statistics, I've already input my data, and I'm going to output this in a, let's put it in a new worksheet. No, let's do it on the same worksheet. Let's put our output in column S. Okay. And make sure that your summary statistics is checked off right here. And then click OK. All right. So when you do that, Excel is going to run a whole bunch of calculations, and it'll come up with some information that's useful for us. In this case here, I'm interested in the standard deviation. So this is information that you're looking to add to your formula, your SX and your SY. So we have your sales calls, you have your standard deviation for your copiers sold. Now you can go ahead and plug those into your formula. Okay, so I'll come back this way. And now let's finish up calculating our R. So we're interested in R equals, and I'm going to use the formula we have up here, which equals to 6672. And I'm going to divide that by our n minus 1. N was, we had 15 sales representatives, so n would be 15 minus 1 multiplied by those standard deviations that we calculated here, multiplied by this value, multiplied by this value. Okay, and I'll put an additional parentheses around everything in the denominator, and I come up with this value here of 0.864. Okay, so this is our R, our correlation coefficient, and this is a number that you want to use to explain the nature of the relationship between those two variables. Okay, so how do I go about interpreting this? and 86 tells me this, first of all, is positive. So these are the things I know about that the number. The number is positive, and it's close to 1. Okay, so with those two pieces of information, I can go ahead and summarize this and say that the correlation coefficient shows a very strong positive relationship between the number of sales calls made and the number of copiers sold. Okay. If, on the other hand, I did this calculation and I ended up with a number which was negative, a negative 0.864, then I would conclude that there is a strong negative relationship between sales calls and copiers sold. Okay, but in this case, we know that the relationship should be positive, and that's what we're expecting, and that's what our results show. Okay, so that's how we go about calculating your correlation coefficient in Excel. And please take a moment and try and calculate this on your own and try and see if you can you can come up with the different data values that are found in your PowerPoint presentation, and then try and test yourself in using the descriptive statistics option that's found up in data and under data analysis. Okay, so with that information in mind, the very last thing that we would look at when you look at correlation analysis is to test for the significance of your R. Okay, and now this last part here is basically based off of the assumption is, yes, we've come up with a value of 0.864. But what if this value was by chance and that our sample was not representative of the actual population? So we have 15 salespeople. The company could have 150, it could have 200 salespeople. What if the sample we took does not fully represent the actual population? So there's a possibility that there could be an error in the sampling. Okay, so we need to test using the hypothesis testing method that was covered in the last module. We tailor it to testing the significance of R and try and come up with whether or not we can rely on this value of R of 0.86. Okay, so how do you do that? First, we have to state what's our null and alternate hypothesis. Okay, and the null here, if you remember what we said, your null will always have an equal sign. So if you're trying to figure out how do we go about writing this down, remember that your null hypothesis will always have an equal sign in it. Okay, so here we're trying, what we really want to know is whether there's a difference in the correlation in the population. Okay, so your null here is that the correlation in the population is 0. Okay, meaning that the correlation that we've gotten from our sample almost exactly equals the correlation in the population. Okay, and the alternative to that is that the correlation in the population is different from 0. Okay, so you bring those two together, and then you go to your step 2, which is determining what's your level of significance. Again, we use most commonly a significance level of either 0.01 or 0.05. Okay, and with that value, you can then go into your appendix at the back and look up the test statistic that you'd be using to try and determine whether or not the correlation is different from 0 or not. Okay, now you're going to use, for this example here, test statistic or the t-test statistic. Why? Our sample here is very small. Okay, it's not as reliable as we would want it to be. So anytime you have a sample less than 30, which might have a normal a distribution that looks like a normal distribution, consider using the t-test statistic first, because it gives you slightly more leeway, and it's more useful when you have small sample sizes, when you're trying to make a deduction on the basis of a small sample size. So here we'll use the t-test statistic, which means with this significance level of 0.5, you'd go into your students' t-distribution on page 518, and look for the confidence intervals at 1 minus 0.05, which would be a 95% level of confidence. Okay, so we're going to look for two. Let me write this down on the screen. When you go into your table here, you need to know your confidence interval. You need to know your degrees of freedom. The degrees of freedom are based on the number of variables that you have, that you're looking at. In this case here, we're looking at two variables. I'll pull out my pen. So we're looking at the number of calls, and then we're looking at the number of copiers sold. So we have two variables, and our degrees of freedom will then be n minus 2. Okay, so that's 2 would be related to the number of variables that you have that you're trying to consider. Okay, so going down on your left-hand side of the student C distribution table, I'm going to look at, we had a sample size of 15 minus 2. So I'll go to the row with 13 degrees of freedom at 95% confidence level, and that gives us a figure of 2.16. Okay, so let me clear all this. So your t test statistic will equal 2.16. Okay, now this is a two-tailed test. Why? Because if you look at your null and alternate hypothesis here, you have just an equal sign. You don't have a greater than or equal or a less than or equal. And whenever you have just the equal sign in your null hypothesis, you're always looking at a two-tailed test. Okay, so what that means is that you have, you're trying to ensure that the correlation in the population, you're trying to test whether the correlation in the population falls somewhere within, again, this region right here. So if this was a sample mean, you're hoping that your population mean will fall somewhere, anywhere within this region here. And that way, you can come up with a conclusion that the correlation in the population is 0. Okay, so let's go ahead and test our t statistic of 2.16. Let's go on to step 4. Okay. Clear all this, and now we go and figure out what's our decision rule. Okay, and our decision rule is based off of this t values of 2.16 on the upper end of the spectrum and negative 2.16 on the lower tail. Okay, and our decision rule is that we will reject the null hypothesis if the value, if our t, get a pen again, falls either below negative 2.16 or above 2.16. Okay, all right, so let's look at our calculation of the t-test statistic. Okay, so the t-test statistic, let me go back to Excel and let's do it here. I'd rather you do it, or you do everything on one page to make for less of a headache. So let's have our calculation of our t statistic here. So t-test is given by this formula that you have here, and I'm just going to replicate it here. So our t-test statistic takes the r that we calculated here. So let's do this. Our t-test statistic would equal r multiplied by the square root of n, which is the number of data points in your sample, which was 15, square root of 15 minus 2. Okay, your degrees of freedom, kind of. And I'm going to divide all this by the square root of 1 minus r raised to the second power. which is R squared. Okay. And that gives you a number. Let's highlight that in yellow. Okay. Let me copy this so that you see what it is that I'm doing here. I'll paste that here. So we've calculated our t-test statistic, and we get a t-score of 6.205. Let's get rid of all those. Let's bring this down to 2 decimal points. So we get a t-score of 6.21. Now I'm going to compare this 6.21 and with what we had in step 4. Okay. And in step 4, we had said that our decision rule was that we'd reject the null hypothesis if our t value was either less than negative 2.160 or greater than 2.160. Okay. Now, our value of t is 6.216, and that would let me get a pencil one more time. That means that that value falls somewhere in this tail, somewhere out here. Okay, so it falls in our rejection region. And what does that lead us to believe? It leads us to make. It leads us to conclude. Okay, that there actually is a correlation in the population. Okay, so we can go ahead and work with a sample and say that yes, this sample actually does have a correlation which is mimicked within the population, the general population. Okay, so that's your correlation coefficient, and that's the gist of what I expect you to get out of correlation analysis. The second part to the chapter is that goes into a discussion of regression analysis. Okay, and regression analysis is one of the most commonly used tools in business research in various aspects of academia. And hopefully after this discussion, after you go over the chapter, it'll make slightly more sense, and you can find ways to make it applicable to whatever business situation that you're working in. Okay, so a regression analysis now takes it a notch higher than correlation, and we now try and estimate one of those two variables on the basis of the other variable. Okay, now let me explain this better. In correlation analysis, we say that yes, there's a strong relationship between the number of sales calls. Let's go back to here. So we say that there's a strong relationship between the number of sales calls and copiers sold. Okay, but we do not actually assign causation in correlation analysis. We just say yes, there's a strong relationship, but that does not tell us whether the relationship is such that copiers determines the number of sales calls, or is it sales calls that determines the number of copiers sold. Okay, so regression analysis now takes it a notch further. So rather than just looking at strength of relationship, direction of relationship, we now say, can we use one variable to estimate the other variable? Okay, so going back to the spreadsheet one more time, how would this work? Let's assume that I want to believe that there's a relationship between the number of sales calls that a representative makes and number of copiers sold. Could I then find out how many copiers should we expect to sell if a salesperson made 100 calls, for example? Okay. Correlation analysis cannot really tell us that. We cannot determine if we made 100 calls, how many copies can we expect to sell? Okay. But if we run a regression analysis, we can actually make an inference and determine that on the basis of the data that we have, if we made 100 sales calls, we should expect 50 copies to be sold. Okay, so that's what we're going to try and do in this second half of chapter 13 when you look at regression analysis. Okay, things to know here. We have both a dependent variable and an independent variable. The dependent variable depends on the independent variable. Okay, if you're looking at the sales versus copy example, the question to ask yourself is, does sales depend on number of calls, or does number of calls depend on sales? Okay, so if you can answer that question correctly, you'll get your dependent variable. Okay, so I would believe that the sales of copiers depends on the number of calls. Okay, so the sales becomes your dependent variable, and the number of calls is your independent variable. Okay. All right. Here we make an assumption that the relationship is linear. It's possible that the relationship between those two variables might not be linear, but if you want to run a linear regression analysis, you have to make that assumption of linearity. Okay. And there are ways to test whether or not the relationship is linear, but that's beyond the scope of this class. Okay. But for the purpose of this class, let's assume that we believe that there's some form of a linear relationship between the independent and the dependent variable. Okay. And I think it makes sense for us to explain this better with an example. Okay. Now, let's look at the least squares regression line and use this to determine or to predict what some value of y would be. Okay. So the least squares regression approach basically says that data in a regression equation is usually centered about some mean value. Okay, and those values are spread across the whole spectrum, but there's a value for each data point which results in the smallest distance between that data point, smallest vertical distance between that data point and that trend line or that regression line that you eventually calculate. And if we can get the smallest distance between all the different values and that trend line, then that gives us the best line of fit. And that's basically our regression line, which we can then use to try and project out, to try and figure out what would some value be out into the future. Okay, so this goes back to your if you remember the equation of a line where we had, let's do this in Excel. Now open a new tab, and I'll use my pencil to try and explain this better. So if you remember our equation of a line, y equals a plus b x, okay? And we're going to say that a is the slope of the line. Okay, your b right here, sorry, let me switch that around and not confuse the class. A is your y-intercept. Writing with my finger is really hard. But your y-intercept is basically where your line crosses the y-axis. Okay, so whatever value you calculate here for A would be the value where your equation line crosses the y-axis. Your B here is the slope of the line. Okay, and that's basically, you're trying to determine what's the gradient of this line based on a calculation. You can take any two data points on your line and try and figure out the difference between the two y values divided by the two x values, and you'll come up with a slope, a value for the slope. Okay. So with that basic example, let's try and work through an example and try and come up with an actual regression. So I'm going to take the same example we had here, take this data, paste it into, oops, it's not gonna work. and I'll call this tab regression. Okay, now we want to use the information we know about the line to come up with an estimate of different values of y. Okay, so when we're going to be coming up with those values of y, we're going to be coming up with estimated values. And in regression term, that's called y hat. Okay, it's y with a slightly curvy line on top of the y. So we're going to estimate a value for y using the information that we have here. Okay, so let's go ahead and do that. Okay, we can decide to do the long route and try and come up with different values of, and calculate the value of A and B. But I would rather use Excel to help you do this. Okay. So the first step was, again, determining what's your X, what's your Y. X is your independent variable, and Y is what depends on X. So your number of copies sold depends on the number of sales calls the sales representatives make. Okay. Now, how would I go about determining the slope of that line just on the basis of this two information in Excel? I'd highlight this information, go back into data, and data analysis has a tool called regression that it's automatically populated. First, I'd input my Y range, which would be this data set right here, this column, and my X range is a sales column. Okay, and I'm going to have my output range on the same tab. So let's, wrong place. And output, let's have our output in H. Okay. So Excel is going to run a whole regression for you, similar to what Minitab or SAS or SPSS would do. And it will come up with a whole bunch of information. It has at the very top here your multiple R. Now, if you look at this number here and go back to your correlation tab and look at your value for R, that's exact same figure that we have for R. Okay, so your multiple R is basically your correlation coefficient. Okay, then you have what's called your R squared, which is basically you taking your multiple R, squaring that value, and come up with a figure for your R squared. And I'll discuss that because that's an important value for any regression analysis. But what we're interested in here again is we wanted to derive the slope of this line. And to do that, you go to the very bottom right here, where you have your intercept and your X variable 1. Okay, so this is your y-intercept, and what you have here is your slope. Okay, so we have information associated with your y-intercept, information associated with your slope. You can use that information. If I had some individual B who made 100 calls, I might be interested in knowing how many copies should we anticipate they would sell if the pattern holds true. Okay, now I could use this information here and come up with a value. If you remember, the line equation was y equals a plus bx. Okay, so let's use that information for the line. So y equals your a, which was your intercept, plus your b, which is your slope, multiplied by your x value. This is column B is your x value, and it gives me a figure for what the number of copies sold would be. Okay, so it's a pretty straightforward way of calculating a regression, and trying to make an inference about some future potential, or not future, but some value of y for any given value of x along that regression line. Okay, so again, how did I get this table here? I got my data, I went to data analysis, regression, and then I input my y range, and then I input my x range, and then I chose a place where I wanted to, I clicked on cell H1 for my output, and then clicked OK. Okay. So that then gave me this table here with the information that I was looking for on the y-intercept and the slope. It also gave me information on the correlation coefficient, as well as our R squared, which I'm going to discuss next. Okay. So let's go back to this last part of the regression equation. Now, we also test the regression equation slope for significance. Okay, basically we test whether the slope of the line in the population, and not in the sample, in this population is 0. Okay. If we don't reject the null hypothesis, we can conclude there's no relationship between the two variables. If we reject it, it means that there actually is a relationship between the two variables. Okay. Again, we are going to have n minus 2 degrees of freedom because we have two variables, so 2 degrees of freedom. And we do it pretty much the same way we've done every hypothesis testing. We bring it into the null and alternate hypothesis. And remember here, we are looking at testing beta. Beta is your slope, your b, your slope value here, okay, in the population. And basically we are saying that if b equals 0, then we have no relationship between the number of calls made and the number of copiers sold. But if b or beta is not equal to 0, then there actually is a relationship between the two. Okay. Now, the process is exact same as the process we've done in the past. The only difference is this. This here. We go back one moment. Okay. So the authors made a small mistake here. We again use a t statistic because again our sample size is the exact same sample. We have 15. We have 15 sales representatives who are being surveyed, and we want to determine whether or not the slope is significant. Okay, so why I was saying that there's an error here, which maybe I should move. Not confuse you on, should I move this to a spreadsheet? I was going to be testing what we had here initially. Okay, beta equals to 0, beta is not equal to 0. They changed it into a one-tailed test, and that's really not how it's supposed to be. But anyway, let's continue, and let's continue with what we have in the hypothesis statements over here. Okay, we'll have to change that, at least for the next class. Okay, so you come up with hypothesis statements, you select your level of significance, and then you select your test statistics. In this case, we're using t again because our sample size is very small. You use your t statistic, formulate your decision rule. The decision rule is based on the actual t statistic that you're going to calculate. Okay, and the t statistic is calculated on the basis of this formula here. You get your beta value minus 0. Divide that by your standard deviation value for your beta. And that information, let's get it over here. So your beta is found on the spreadsheet right here. Just a different color. And I can use this, and for standard deviation, you don't have to go far. That information is also already provided in your output. Okay, the standard error, it's bigger. So you have your beta, you have your standard error, standard deviation number value of 0.042, number of decimal points. And with that information, we can now calculate our test statistic. Okay, and we calculate our test statistic, and then you compare that test statistic with what you have from your t tables. In this case here, they've turned it into a one-tail test, so it's being compared to 1.771. If I'd gone with the two-tail test, I would again compare it to 2.160. But either way, we would reject the null hypothesis. And we conclude then that the number of sales calls is useful in estimating copier sales. Okay. So that is a brief introduction of regression analysis. It's a pretty useful tool, and in the next video, I'm going to take it a notch further and discuss multiple regression analysis and how that differs from a simple linear regression. Okay,